Let's apply this false position algorithm for the example that we used for the bisection method. And in the example, if you remember, we were going to use the same parachutist problem with the same parameters, and we want to calculate the C value, the drag coefficient value, using its formula. And we want to continue until the threshold is 0.5%, or our approximation error is below this value. So let's try to apply. If you remember from the example 5.3 or the previous example, we set the initial guesses of bracket, let's say, because it's a bracketing method, and we said xl is 12 and xu is 16. Again, we can find we can actually draw or plot the graph of the equation and see where the root is, and we can set a lower and upper bound based on that. And we did this earlier for the bisection method example. So in the first iteration, we need to calculate, let's say first iteration. So we need the function values of these. That's why if xl is 12, then f12, you can use the parachutist example equation. It was in the previous example. You can just see it from there. 6.1139. Simply we plug these in to the equation. And for 16, f16 is minus 2.2303. You can see that the zero value the zero f value is between these, because one is positive or one is negative. And because we have these, we can simply have xr as the xu is 16. This is xu minus the fxu minus 2.22303, and xl minus xu, 12 minus 16. This is fxu times xl minus xu. This was the formula, if you remember. And at the bottom, the difference of the function values, again 6.1139, which is fxl minus 2.2303. So this is fxl minus fxu. And if we calculate this, xr is equivalent to 14.1309. And if you remember from the bisection example, we used midpoint method, and midpoint gave us the middle point of these, which is 14. And now this is 14.13, sorry, not 13 actually, 309, like this. And this, if we know the actual value of the C, which is 14.9 something, this is closer to that. And you can see that false position actually having a better guess, closer guess to that. And the relative error to this, the true relative error, we find the true relative error as 0.88%. You can calculate this based on the true value. But we don't have an approximation error over here because this is the first iteration. We don't have it. So if we don't have it, if you are using an algorithm writing in MATLAB, for example, you can make this a very large value. So the first EA, epsilon A, will be, for example, 100. Just make it 100, a big value, so that it doesn't stop at the condition over here. So we will go to the second iteration then. By the way, you can see that the true error is very low, even at the first iteration. So let's go to the second iteration. Of course, before going that, we need to check if the multiplication is positive or not. So it is fxl times fxr. So xr is this, xl is this, and the values, of course, this is this value 6 times, and fxr value we need to calculate it. You can simply write it to the function and calculate, and the result is actually minus 1.5376. The result is not important. The important part is the negative sign. If it is negative now, then the root is on the left side, which means we will use the xl again because it's on this side. We will use this, and this xr will be our upper value. Then xu2 is equivalent to 2 is the second iteration, is equivalent to xr1, which is 14.309. Then in the second iteration for xl12, f12 is again the same, 6.1139, and xu is 14.309, and f 14.309 is equivalent to minus 0.2515, 0.2515. As you can see, the upper bound is getting closer to the zero value. This is very close. That's why this time it will probably be closer to the upper bound, because we said that the function value determines whether the root is on the left side or right side, or on the upper bound side or the lower bound side. Here it's on the upper bound side, it seems. With these, we can calculate xr again. You can use the same formulation you used here, and xr value is 14.8151. And with this, if we calculate EA, let's see the E true first. Epsilon true, the error is 0.09%. This is very accurate, as you can see. So this is almost the same as the true value. For the approximation error, for that we simply use the first and the difference between xr2 and xr1, basically 14.8151 minus 14.309 divided by the current 14.8151, and we can just have the absolute times 100, and from here the result is 0.78%. And you can see it is still greater than 0.5 because we want to have 0.5. We can continue further, a third iteration, but I'm not going to do that. You can simply do yourself, but we need this. But eventually, after the third iteration, you will have the final solution with very close EI value as well. So here the true value is very low. That's why we can also set, if we know the true value, we can just stop here as well because it's less than 0.5. But if we are using approximation error, we need to go further and do the third iteration. Do yourself. And you can see even in 3 iterations, it will have the true value. And in the bisection method, if you remember, we use 6 iterations to be able to get the final value with the error less than 0.5. You can see that's why the false position is much closer, much quicker to get a closer result to the actual root. In this slide, we will compare the performance of bisection and false position methods in terms of approaching to the root. So for the bisection method, the interval between lower bound and upper bound grew smaller during a computation. And the interval, as defined by delta x divided by 2, is simply the midpoint for the first iteration, and therefore provided a measure of the error for this approach. So this actually gave an error for this approach, and it has a like half error, let's say half between the upper and lower bound. On the false position method, on the other hand, Getting smaller on both Excel and XU sides is not the case. So we don't have both sides getting smaller. Actually, one of the initial guesses may stay fixed throughout the computation as the other guess converges on the root. So this is called one-sided. So sometimes, for example, the lower bound is always lower bound, doesn't change, and upper bound keeps getting smaller. And this is called one-sided nature. It can be the opposite. The upper bound can be constant, while the lower bound is getting bigger and bigger at each iteration. For the parachutist example, example 5.5, if you remember, the lower guess Excel remained at 12, while XU, the upper bound, converged to the, so it was getting closer to the root, the upper bound. And if you remember, for example, for the bisection, we had 6 iterations, and you can see Excel and XU, it keeps changing. So Excel changed from 12 to 14. It was constant a little bit, but then changed, and then again changed. XU as well changed, and changed. So you can see both can change. In the false position, on the other hand, you can see the lower bound was always constant, and the upper bound was like this, changing and getting closer to the result or the actual value. And you can see the error values here. They are very close, and this is actually true value. So that these are the features of false position and bisection for approaching to the root. We can also make an error comparison for the bisection and false position method results. You can see on the left hand side, the true percentage relative error is decreasing for false position very fast, very steep, and very constant, actually, a linear decrease from error of 1% to 10 to the power minus 4 in 4 iterations. That's very, very small error in the end. But bisection, you can see it's getting smaller, getting a little bit higher, then getting smaller again, higher and smaller, and actually it's converging somewhere over here. So the error value is low, but not as low as the error value that false position can have. So the error for false position decreases much faster than the bisection, and let's ask the question why. And the reason is because of the more efficient scheme for the root location, and the formulation for the root location was only the midpoint for the bisection, while for the false position it was using the function values as well. And using function values gives an idea whether it is on the lower bound side or upper bound side, and makes a quicker decision or quicker convergence to the actual root. And so the reason is because we are using the function value in the formula. So this is a general comparison or general actually behavior. So these errors were for the example 5.5, which is the parachutist example. But this general behavior exists in any problems actually. False position is mostly or always, we can say maybe, much faster and can have better predictions with lower error values compared to the bisection method.